So in this video, we're going to talk about quantitative energy problem solving. First, we need to derive an equation for dissipated energy. So if we think about what factors affect dissipated energy, the force that dissipates the energy is the force of friction. And how much energy is dissipated is going to be how far the object travels, how far it slides. So these two factors affect dissipated energy. Now, how do we find an equation for dissipated energy? Well, how do we always find equations? We make a graph. And so when we graph displacement and friction, and this can, I have displacement here. We could also say distance. It's really not, the vector is really not important. It's how far the object travels along. It's really the length of the path. So this should really be distance. And so we have a force of friction applied over distance, and that force of friction is going to stay constant for our needs. And we are looking for the energy. Now, we have seen a force versus distance graph before. We saw that with Cook's law, and we saw it with when we derived the equation for work. The unit for friction is newtons. The unit for displacement or distance is meters. And so we need to find energy, and the unit for energy is joule. And a joule is equal to a newton times a meter. So if we take the area under the curve, we will multiply newtons times meters. And the area here is equal to energy. The area under a force versus distance graph is always going to be energy. So if we look at the units, we have newtons times meters, and that equals a joule. So let's go down here and we can actually derive our equation. So we have area, and since this is force of friction, that's going to be equal to, area is base times height. So force of friction, the energy associated with this is going to be a dissipated energy. So E dis is equal to the base times the height. So force of friction times the displacement, which it's really distance, but we use a delta x. I guess you could put a d there too. I don't actually remember what your book does, but it's a distance. It's how far it slides. So this is the equation for the dissipated energy. Remember that energy is a scalar, and that's going to help us as we move forward. Now let's talk about the steps for solving energy problems. You've done lots of work with drawing LOL diagrams, and you're going to continue to do that when you're solving energy problems. They're going to help you set up the problem and solve it successfully and make fewer mistakes. So the first thing you're going to do is sketch the diagrams for initial and final situations. We did do some LOL diagrams where you did a bunch of different parts of a motion, but usually when you're solving for problems, you're just going to pick two situations, like two parts. You have to establish your y equals 0 or your 0 reference line, and this is for when you have gravitational potential energy involved. If you don't have gravitational potential energy involved, then you don't actually have to do that. You need to make sure to establish your system, and this can be done in different ways, and you can be successful by doing it in different ways. It doesn't really matter. You just have to be consistent when you're keeping track of all of your energy. Then you want to identify what energies are changing within the system. So you know which energies to put in your LOL diagram. You draw your LOL chart and put those energies with your boxes. Make sure your boxes add up. You might have work going into the system or work coming out of the system. Then you're going to write your energy conservation equation. That's your first law of thermodynamics. So all the initial energies plus or minus work equals final energies. And then you're going to draw a force diagram if you need to. And if you have dissipated energy, you may need to draw the force diagram to determine what the frictional force is. And then you solve for unknown variables. So if you follow these steps, energy problems really aren't too bad. I've got a list of the equations that you're going to use here. We derived these in the lab. So you derived kinetic energy, you derived gravitational potential energy, and you derive spring potential energy. We talked about the work equation, and we worked through that, haha, and then we just came up with our dissipated energy equation. All of these are on the equation sheet. These are all on the equation sheet. This one is not on the equation sheet. So you need to make sure that you know how to find dissipated energy. You can always think about it as work done by friction. It's just the force of friction times the length of the path, the distance. But your cosine theta for that will always be your force of friction and your displacement are always going to act in opposite directions. So your energy is always going to be coming out of the system. So you're going to get a negative sign there, but you can use it to find the absolute value of the dissipated energy. Also remember that negative work does not mean, the negative does not mean a direction because it is a scalar. It just means that energy is leaving the system. Okay, so let's give it a try. This is a problem you could actually solve with kinematics, but we're going to solve it with energy. So we have a ball that has a mass of 2 kilograms, and it falls a distance of 3 meters. So, and we want to determine how fast it's going when it reaches the ground. So we have our situation drawn. We are going to establish our system. So I'm going to put the ball in the system, and I'm going to put the earth in the system. And you have to put the earth in the system when your object is changing its position in the gravitational field. We also have to establish a 0 reference line, because remember that only changes in gravitational potential energy are going to be important. The absolute gravitational potential energy is not important to us. So we usually, the lowest position of the object is going to be the best place for the 0 reference line. And then we're going to think about what, I'll put y initial equals 3 meters, although I don't think I'm going to actually solve these out to save us some time. So we need to think about what energies are changing. So in this initial position right here, we have gravitational potential energy. And in this final position here, we have only kinetic energy because it is moving. It's like right before it hits the ground. And there's no dissipated energy. We're neglecting air resistance and all that. So initially, I just have gravitational potential energy. And at the end, I just have kinetic energy. So now I write my first law of thermodynamics equation. Gravitational potential energy equals kinetic energy. And then I substitute in my equation for each type of energy. So mass times gravitational field strength times height equals 1/2 times mass times velocity squared. What happens to our masses? They cancel. And mass will usually cancel if you don't have, as long as you don't have friction, mass will usually cancel. Well, that's not true. If you have spring potential energy. If you're just working with gravitational and kinetic, it would cancel. And then I forgot what we're solving for velocity. So we solve for velocity and we get velocity equals the square root of 2gh. Now, that may look familiar to you. Let's think about this situation using kinematics. So let's do it again using kinematics and see what we get. So if we're using kinematics, we have our initial velocity is equal to 0. We're looking for our final velocity. We know acceleration is equal to g, and we know that the change in y is, oh, why did I put an h there? Yeah, we've been using y in this class, sorry. It's different in different physics classes, so sometimes I get them screwed up. Many physics classes use an h, but we usually use a y in AP Physics 1, so let me change that. Sorry, okay, so this is mgy, and this is square root of 2gy. Okay, so our delta y is going to be just y. And I'm going to choose down as positive for this. So I set up my equation, and this is, I don't have time, so I'm going to use my equation without time, which would be v final squared equals v initial squared plus 2a delta y. And then I plug in the things that I have. I know my initial velocity is 0, and I'm solving for v here. So I get v squared equals 2 times g times y. and then I do v equals the square root of 2gy. So we get the same thing. Isn't that so cool? Using kinematics and using energy, which is great. Now I would encourage you to try to use energy as we're practicing these energy problems in this chapter, but on a test, on the AP exam, you can use whatever method you want to use to solve problems. Okay, now let's think about another situation. So here we have a ramp, and this block is sliding down the ramp. I know there's some complicated things with it coming off the ramp, but let's just pretend like it's not complicated. Actually, I kind of would prefer to have this. Oh, it's all together. Okay, well, I'm not going to mess with it then. Okay. Okay, so our initial velocity up here, no, it's sliding up the ramp because this is v1. And how high does it go? Great. So our velocity down here is 3 meters per second. Mass is 10 kilograms. It is frictionless, and we want to know, oh, the velocity here is 0, so we want to know how high it goes. So what we need to do, we have our picture drawn. We need to think about what's going to be our system and where our zero reference line is, because the height of the object is changing. Its position in the gravitational field is changing. So I'm going to set this as my zero reference line, and I'm going to put the block and the Earth in the system. And then I'm going to think about the energies that I have involved. So initially, I have gravitational potential energy. Oh my goodness, that's not right. Like, for some reason, I have it in my head that it's sliding down the incline. Okay, so initially I have kinetic energy. And I'm just going to give it 3 blocks, and at the end I have all gravitational potential energy. And it's frictionless, so there's no dissipated or anything like that. So now I'm going to write my first law of thermodynamics equation. K equals UG, and our K is 1/2 mv squared, and our gravitational potential energy is mgh, or mgy, excuse me, goodness. And then our masses cancel. So we're solving for y in this one. So y is equal to v squared over 2g. And then I could use that to figure out how high it goes. Now, when you're doing problems like this, it's also important to think about the fact that you're going to get the vertical change here, this y, when you're doing the energy equation. There may be problems where it asks you for how far along the incline it slides. And you would have to use trig to figure that out, because the energy equation will give you this height. So my next question for you to consider is how does the height change if theta increases? So let's say that I now have a steeper slope. If I were to do this problem again, notice that theta is not in my equation at all. So the slope of the angle of the slope does not matter. The height will be the same. So if I have this block going up a slope like this, and a slope like this, and a slope like this, they will all get, well, that one's like not long enough here. Like, all of those blocks would get to the same vertical height. So maybe here's a block, and let me draw my line so that I know what's going on here. Needs a sound effect. That's supposed to be horizontal, just pretend that it is. And this block would get to here, and this block would get to here on this one. So they would all get to the same height. They would go a different distance along the ramp, but the heights would all be the same. So the angle of that isn't going to matter. Now let's do the same problem with friction. So now let's say the coefficient of friction is 0.3. So the first two that we did were pretty simple, and now it's going to get a little bit more complicated. Okay, so we have our situation. Ooh, I fixed this picture. I should go back and fix the other picture, but here's our situation. Our initial velocity is 3 meters per second up the incline. Our coefficient of friction is 0.3, and we want to know how high it goes. So we want to know this height right here, h. Okay, so we're going to put the block and the Earth. And I'm going to put the surface in the system as well. If you want, you could put the surface outside of the system and think of that as an external force doing work, doing negative work, taking energy out, and that would be fine. You can do it different ways, but I like to keep a closed system if I can personally. Okay, so initially I have kinetic energy. And then in the end, I have some gravitational potential energy. And I have some dissipated energy. There's no more kinetic energy because it is no longer moving. So then I write my equation, K equals Eg plus E dis. And then I can expand it into 1/2 mv squared equals mgy, which is really h in this case, but we'll just put a y, plus our dissipated energy, which is a force of friction times the length of the path. Now this is where it gets a little bit complicated. So this right here is the delta x. So I'm going to go ahead and just write that here, and then we're going to expand it a little bit. Okay, so we want to solve for y, this is y or h, but we have a delta x in there too. So we're going to use a trig statement where the sine of 30 degrees is equal to, I'm just going to call that h, over delta x. And then we're going to solve for delta x. Delta x is equal to h over sine 30. So I'm going to put that into my equation down below. Additionally, I have my force of friction equals mu times the normal force. So I need to know what the normal force is. Now, in order to do that, I need to draw a force diagram. So I draw a force diagram. Isn't this so great? You're getting to apply, you already applied kinematics, you get to apply forces again. We have our force normal, we have our force of gravity, and we have our force of friction. And my x-axis is here, and my y-axis is here. Oh, I probably should have switched to a regular pen there. And then I can split my gravity into components. So this is FGY, and this is FGX, and this is theta. So the sum of the forces in the y direction is equal to the normal force, and I'm going to do this without vectors, minus force of gravity in the y direction. And that's equal to 0 because the box is not accelerating in the y direction. So my normal force minus force of gravity in the y direction is going to be mg times the cosine of theta, because it's the arm that's close to the, or adjacent to the theta. And so we get normal force is equal to mg cosine theta. All right, so there's that. Now that's going to be plugged in down here. All right, so let's see where we are. 1/2 mv squared equals mg, that y I'm going to change to an h, plus force of friction, which is mu, times the normal force, which is mg cosine theta, times our delta x, and our delta x is equal to h over sine theta. And we are solving for, I believe, h. Yes. It's been a long time since I looked up there. All right, and our masses cancel again, woohoo. And then we need to isolate h. So we have 1/2 v squared equals h times g plus mu g cosine theta over sine theta is going to be cotangent theta times h. Okay, and then I pulled the h out. I think I got that right. Mu g, okay, yeah. And so then we get h is equal to v squared over 2 times g plus mu g cotangent theta. Okay, so now I can plug in numbers. We get 3 meters per second. We square that. We divide by 2 times 9.8. I probably could have pulled out my g too. I'm going to pull out the g. Times 1 plus mu, which is 0.3. Yeah, 0.3. Times cotangent of 30 degrees. Okay, so then we would get, I can't find my answer. Let me calculate it real fast. You can just fast forward through this part, right? You still fast forwarding? Okay, I think I got it. Maybe. Okay, I got 0.3. I'm not positive that's right. That's not what I don't know. I didn't write down the answer apparently. Okay, so then we can calculate our height from that, which is how we do that. So that's, you can see that that's a considerably more complicated problem when we add friction. So